Okay, here we go again with heat, temperature, and atmospheric circulation. So what we're going to deal with mainly is temperature today. We got all this energy that's come into the atmosphere from the sun. What are we going to do with it? So that's where temperature comes into a play. So how does that heat, now that heat is basically the transfer of energy. So we're going to deal with the transfer of all that sun's energy within the Earth atmospheric system. Guess what? It can be pretty complex. You're going to get a little sample of it. So first thing we're going to talk about is temperature. What is temperature? Temperature is the kinetic energy, basically, of an atom or a molecule. What do we mean by that? Well, the electrons rotate around the nucleus, and with that, they can rotate faster or shake more. And when they do that, that produces kinetic energy. So that kinetic energy is a measure of temperature. When we deal with temperature, we have 3 different temperature scales. We have a Fahrenheit that you all are used to seeing because it's an English scale. It's old. We have Celsius, which is a more modern scale. And we have Kelvin. Kelvin is basically, that temperature is proportional to the kinetic energy of an atom or a molecule. So if you measure the temperature in Kelvin and it gets to 0 degrees Kelvin, you're saying that there's nothing left, no more kinetic energy in that molecule. That's really what you're saying with that temperature. And guess what? Kelvin and Celsius make it a whole lot easier to do the math that comes with this. And heat is just energy and transfer. So one of the things we talk about here too is the change in temperature over distance is a temperature gradient. So if you're dealing with a temperature gradient, you want to look at how close together the temperatures are, how fast they change. So say you were driving across the state of Ohio. As most of you are from Ohio. Let's start in Cleveland. We'll say the temperature in Cleveland at this time was 70 degrees. You drive on to the west and you reach Toledo and the temperature is 40 degrees. That difference in temperature between Cleveland and Toledo is a temperature gradient. And you know the distance, so you know how fast that temperature changed. Now, if Cleveland's temperature was 80, Toledo was 30, that would be a stronger temperature gradient because it had changed faster. It was more of a temperature change over that same distance. All right, so heat flows in response to that temperature gradient. Guess what? Heat is always going to go from the warmest to the coldest. So in other words, the heat transfer is always trying to get rid of that temperature gradient. Nature, God, when he created this all, decided that gradients weren't a good thing for whatever reason. So one of the things in weather is that all gradients are trying to be gotten rid of. They never are. That's why we have weather. Keeps me in a job. But there are different ways heat can flow within the atmosphere too. Radiation, which we talked about a lot in the earlier one. Conduction, convection, and latent heat. Radiation is just energy, forms moving along as waves transferring across areas. Conduction. All right. If you walk outside in the summertime and walk over a very black surface, say asphalt, I bet you that if you put your hand down on that asphalt, it's going to try to burn you. It's going to feel very hot. That heat is being transferred from that asphalt into your hand. That's conduction. Think about it when you're heating a pot on a stove. The gas or the flame or the electric heat, either one is transferring through the pot, heating what's inside that pot. conduction. Convection. In the atmosphere and any fluid. So if you heat a pot of water, you always watch these bubbles that are coming to the top. Those bubbles that are coming to the top are convection. The hot heat that's being produced at the surface and being pulled to the upper surfaces actually cools as it rises because it's getting cooler and cooler the further up it goes. And then it sinks back down and restarts the process in the atmosphere. Sensible heating is just conduction and convection together. It dominates much of the heat transfer in the atmosphere. There's one other piece to this, though. Because we have water vapor in the atmosphere, and water vapor actually holds a tremendous amount of energy, it causes more heating transfers. So, if you go from a vapor to a liquid, let's just go that direction to start with. So you're condensing it. A liquid, the molecules are not moving as fast as they are in a vapor. So that means there's less kinetic energy in a liquid, even though there might be the same temperature. There's less kinetic energy. Heat has been released if you have condensation. So that means that any time a cloud is forming in the atmosphere, heat is actually being released into the air. It's warming the air around it. Now, if you go from a liquid to a solid, the same thing's happening. Those molecules aren't moving as fast. They're going to, again, be a transfer of heat being released. That's latent heat. Now, go the other way. If you go from a liquid, say you have a rainy day, you have all these puddles on the ground, or you've had several days of rain, the atmosphere, the sun starts heating it up. What happens? The sun's energy is going to go into evaporation. Well, that's going to keep the air cooler because evaporation is a cooling process. That's why a maritime climate like San Francisco is going to wind up not having as much temperature change as something over the continents, because the water really takes a tremendous amount of energy to heat up. So it doesn't change dramatically normally in big oceans. Now, here is just a quick example of all the ways energy is transferred in the atmosphere. And you can see, wow, there's a lot of different ones. They all got to equal each other out. All the energy coming in must equal all the energy going out. So you can see heat transfer sometimes in the summertime with thunderstorms. Heat's being pushed up from the surface. Air parcel is being heated. Here's another one. The solar radiation, we talked about it. There's a surplus compared to the actual temperatures that are occurring down around the equator to just the two tropics, Capricorn and Cancer. There's a surplus of solar energy coming in while there's a deficit further up towards the poles. That means that something's got to transfer all that excess solar energy down there to smooth things out because there's a temperature gradient there. What are some of those things? They're air mass exchange, storms, ocean currents. Guess what? Hurricanes are one of the most efficient and best ways of bringing heat from the tropics into the northern latitude. So air masses are basically just a large mass of air, uniform temperature, uniform humidity usually. When these air masses then move, when they move over land or whatever, maybe they're being modified from below. Maybe the land is warmer, it's going to tend to modify them, or maybe the land's colder, maybe getting rid of the hotter air masses. But there's going to be temperature transport in that kind of an air mass motion. And there are storms as well. And this imbalance is what causes all the weather that we have to deal with. And here you can see how that goes during a day. If you ever walked outside and ever thought about temperature, you probably don't think about it that much. Lowest temperature around 6 o'clock in the morning, we'll say, on a normal day. Notice up until that time, infrared radiation is going out, so the temperature is dropping. Sun rises. There is still a point in time where more infrared radiation is going out than actual solar radiation, UV radiation, is coming in. That's why the temperature actually reaches its minimum slightly after sunrise normally. Now, the temperature is going to go up quickly because the sun's coming in. It's going to continue to warm it. And the ground's fairly cold, so there's not as much infrared radiation going out. So it's going to warm up quickly. And then gradually the grounds are going to heat up, so there's more infrared radiation going out, but there's still enough solar radiation to reach the maximum temperature, usually in mid-afternoon. After that, as we get towards sunset, once the sun sets, you lose all that solar radiation. And guess what? The ground's really hot, so the infrared radiation is really going to be going out very strongly at that point. Temperatures are going to drop pretty daggone quickly. So the first few hours after sunset, temperatures are going to fall the fastest and then slow down as the Earth cools. So that is how the local radiation budget works with all of this. Bare ground is going to have a lot more sensible heating, conduction, convection. Snow cover, if you have snow-covered ground, you have great albedo. You're sending all that energy back into space. That's why very cold air that comes in after a big winter storm sometimes keeps very cold. If that same air mass had come over, continued over bare ground, it would be warming. A lot of times I can watch your high temperatures in Ohio, where you have the snow cover maybe in the wintertime, are in the teens, in the low 20s. By the time that same air mass makes it to my house, where I haven't had the snow cover, I may be having highs in the 40s, even low 50s. So that bare ground makes a big difference. There are urban heat islands. Here is Washington, D.C., and you can see how the more concrete will actually cause the temperatures to be higher in those areas. And they'll stay higher at night because all these urban heat sources absorb, and instead of sending the temperatures out at night, they actually keep it warmer. That's why the big cities have warmer climates at night and stay pretty warm during the day. So with that, I just wanted to show you one quick thing here on this. And here's the surface temperature this afternoon. Cold front is right here. And we talk about temperature gradient. Temperature here is 77, 84. Yeah, it's pretty far distance, but that in the summertime is the temperature gradient. There's going to be a 81 here, 88 here. So there's about a 7-degree temperature gradient across this front. It's cooling you off. So as that cold front, and this is a Canadian air coming in, warming you, bringing you cooler air. And here are the lakes. Remember we talked about latent heating? Lakes don't exactly warm very fast. Notice these temperatures in the lakes. Here's 60 degrees, 61 degrees. That's because the lake is staying cold. The air moves across that lake. It gets cooler because the lake is so daggone cold. Here's a warm front, 68, 61, warm front pushing north. There's warm advection here, cold advection here. And on one final thing, I was just going to show you it. Here's the current. Temperatures are in red here. Here's your cold front that we just looked at, and here's your temperature gradient, and you can see very tight red lines together. But look at over the waters. The Great Lakes are cold. You can actually see a very tight temperature gradient over the Great Lakes. And guess what? There's one in the Atlantic Ocean, right along the Gulf Stream. So, hope you get something out of all this, and please don't hesitate to ask if you have any questions.